Welcome back, dear students. We are learning computer graphics and multimedia. In the last class, we discussed about various graphic systems, input-output devices, different display devices, and storage devices. Today, we are going to discuss about Introduction to Computer Graphics in the chapter 1. This is part 2. Here, we will discuss about the 2D transformation. And most importantly, we will understand what homogeneous coordinates are, what are the different types of 2D transformation like translation, rotation, scaling, as well as there are two more things like reflection and shearing. But in this class, we will restrict ourselves about the discussion of translation, rotation, and scaling. And we will also come to know about the matrix representation of these above things. Start with the 2D transformation. Transformation means changing some graphical shapes or position, right? So what are the different types of transformation like translation, shifting the place or changing in the position. Scaling means either the shape of the entire object is either increased or decreased. Then rotation, if this is the object and it is rotated clockwise or anti-clockwise, that means all these things comes under the 2D transformation. Okay, and as well as the few more things are there like reflection and shearing. So let's start our discussion on these topics. Now we need to know about what homogeneous coordinates are. Basically, if we have a two-dimensional diagram, that means the coordinates are x and y, then there is a way of representing this two-dimensional figure in a three-dimensional way, or we just add one more coordinate, right? So if we have an object that undergoes multiple operation which include translation as well, as in this coordinate system translation is also represented as multiplication. So a 2D translation matrix can also be represented in a way that this translation matrix can be represented in a matrix form which supports the multiplication factor. So how we can represent this? This is the way how we can represent the translation as a multiplication factor. So simply we add another term h here. It can be told as w or whatever you like, but the basic idea is we are putting another dimension here. It means if we are having a point P at xy coordinate and P dashed at xhyh coordinate, and h is the factor, so we can write x is equal to xh by h, so x into h, that is equals to x suffix h, and similarly y is equal to y suffix h by h. So if this thing we want to represent in a matrix form, in a 3 cross 3 matrix, then this is the another dimension that we have added as h. So we simply uh, divide h by h, so it gives 1, so that is why here we have 1. So x and y is the old coordinates and x dash y dash will be the final coordinates after translation of any object, right? So object may have many points in it, so any one of the point will be translated towards a particular position. So this is one of the points, final location will be x dash y dash, and this is the matrix representation of that, right? So let's move on. Today's discussion will confine to 2D translation, 2D rotation and 2D scaling. Here we have, first, to understand translation. Translation is moving in a straight line. So any point which was here, it is now placed at some other location, provided there will be no structural change. That means the size will be intact. So each and every point present on a particular object will also be at the same position, but after some displacement. So it traverses a distance d after translation, but the original size of the object will remain intact. Now it has the traveling of distance following a straight line. So the initial position of the point and final position of any point on that particular object, if we consider this is P and this is P dashed, so P dashed will be having some x-axis movement and some y-axis movement. So finally the x dashed value will be calculated as x plus tx, that is translation shifting value, and y plus ty, that will be y dashed. So we'll detail about translation in later slides. So here we just need to have some overview of the other things. Here rotation and scaling we will also mention about. So this is how this rotation occurs. We are considering it as the angle q, right? Q is the angle, and from this point it is rotating and moving up to this particular point. So if it is P and this is P dashed, so we have to calculate what will be the coordinate, final coordinate from P and at this point P dashed. Okay, so if we know the angle Q, then we can easily calculate it. Okay, so that we will discuss after some slides as well. And scaling is the change in size, and the change in size could be like initially it was x, right? And after scaled up, that same point is located at some different location. So there will be a scaling factor, and that we consider it as sx. So x into sx will be giving us the scaled up or scaled down final point position or coordinate, right? So this is P and this is P dash if we consider. So we can calculate the x-axis value of this particular point using s into x dash, and similarly y is equal to y into, sorry, x dashed is equal to s into x into sx, and y dashed is equal to will be y into sy. Okay, y into sy. So this is the way how the scaling factor works. Now let's discuss about the 2D translation. Here let's say P is the first point, this is the point, and from this particular point it is moving in this direction and it reaches to Q. So what will be the coordinate of Q? Let's say the initial coordinate was x0 y0 and the final coordinate is x1 y1. So x1 minus x0 will be tx and y1 minus y0 will be ty. So that is the deflection in x-axis and y-axis for this point P and Q. And the translation matrix will be looking like this. X nu will be x nu and y nu will become like this. If we add this tx and ty, it is a plus over here. Instead of plus, this translation can also be represented in a matrix multiplication form that we already come to know in this particular homogeneous coordinate system. So we will again discuss the same thing here, right? So If we look into these particular pictures, we will be able to clarify that what translation is. Translation is nothing but change in position in x and y plane. Very simple. Here, the distance between two points before and after translation, right? So let's say P and P dashed. So this is the first point P and this is the last point P dashed. So in between these 2 points, we have to calculate the distance. So after moving to P dashed, if the coordinate of a point is x dashed and y dashed, then we can easily calculate it. So the initial coordinate was xy. With that, if we add tx and ty, then we'll get the final coordinate, right? So here in the first image, this portion, it is a positive translation. Why it is positive? Because the direction is away from the origin and it is within the x-axis and y-axis. So this is y-axis, this is x-axis, and here is the movement of the point P towards this direction. That is why it is a positive translation. If it was opposite or reverse, like in this case, this is a negative translation because this point P is moving in the reverse direction than that of this one. Okay, that is why it is called a negative translation. So what translation looks like? In the image, if we see this particular blue triangle, it is supposed to move following this particular line. Okay, so we'll look into the animation as well. Now here first, how to denote this particular translation matrix, right? With the help of this matrix. So this is the matrix where we have in the diagonal there are ones, and here we have px and here we have py for positive translation, and for negative one minus tx and minus ty. As simple as this. So this is the animation where you can see the movie that the blue triangle is shifted from left to right. Okay. So this is what the translation is, means shifting the position. Now we'll discuss about 2D rotation. Now rotation is a kind of thing where a point was there which is just moving toward left or toward right. That means either it is moving in anti-clockwise way or in a clockwise manner. So the rotation takes place in the coordinate system. Let's say this is x coordinate and this is y coordinate, and O is the initial position of any point, and that point is supposed to be shifted to some other point after this rotation. And you see this is the rotational guideline, right? And it follows a rotation of amount theta degree. So if it is rotating by theta, that means what exactly happens, that this point is supposed to be in a different location. Now let's see how it can be denoted, means graphically, or this is the graphical representation, and in using matrix form how we can calculate it. Okay, so look at this particular uh, diagram. What exactly happens here is that P is a point vertex of a triangle, this one, and it is rotating in this direction by an angle of theta. So this is the angle of theta rotation, and this is the anti-clockwise rotation, and it reaches, the vertex reaches to point P dashed. So if we have the final point P dashed, then that point coordinate, that means the initial value may be x0 y0, and we have to calculate x1 y1. So that is the coordinate of P dashed, or it could be x dashed y dashed as well. So how to calculate it? So this is the formula for calculating this particular uh, final position of p dash. There is a point on any object which is uh, undergoing a rotation of theta degree in anti-clockwise direction. And if it is anti-clockwise direction, it is called a positive rotation, or if it is in clockwise direction, it is a negative rotation. And the matrix that we can interpret, this is the positive one, that means anti-clockwise, ACW. Okay, and this is the matrix for clockwise, so it is you can say -1. Fine. So these are the two matrix representation of this rotation. Now, if we can give you an example, how or what will be the final representation of this point P, and that P is going to be rotated and finally reaches to a point that is called P dash, right? Now, how to calculate the answer, that is P is 100, this is the uh, coordinate point, and how it becomes after 30 degree of rotation, how it becomes or located to this particular location. Now 30 degree, so here it is in anti-clockwise direction. So what is the value of cos 30? Cos 30 is something like √3/2. And what is the value of sin 30? That is 1/2. Okay, that is 1/2. And then again sin 30, so this is negative. Then again sin 30 is half, and again cos 30 is √3/2. Okay, so √3/2, this is something somewhere the value comes 0.87. Okay, 0.87. So 0.87 minus that is 50, that gives us, you can say, 37. If we calculate it, we will get the exact value like this, 37. And this is 50, because by 100 it will be multiplied. So 0.5 into 100 is 50. 50 plus this one is 87. So it gives you 137. So that is how the final value of this P dash is calculated as 37, 137. That is the rotation happens. And if it is in a clockwise direction, then this signature or the sign is changed, and accordingly the final value will be calculated. Now coming to the next topic, that is called 2D scaling. Scaling means there will be a change in shape, or better to say the size will be changed. Not the shape, but the size will be changed. Like in shearing the shape could be changed, but in scaling the size is changed. That means if it is a rectangle, it will again be a rectangle, but the size is changed, means it is doubled, it is 1.5 times, it becomes 2.5 times, it becomes half, it becomes quarter. The size is changing. Now while the size get changed, then each and every point of an object, let's say ABCD is a rectangle, and is vertex like A, B, C and D, they are at this position initially. Now the object is having P0 position. So after scaling, it will have a position of each point, like A becomes A dash, B becomes B dash. So every point will be having a new coordinate, and that coordinate value will be calculated by just multiplying with Sx or Sy And what these Sx and Sy are called, these are like scaling factor with respect to x-axis and y-axis. So this is the matrix how the scaling can be calculated. So the new coordinate of x and y of any point of object of this object can be calculated using this formula. So it's a calculation matrix multiplication, we can say. So this is how we can calculate the final value of the coordinates of every point of this object ABCD, and finally we can get the values. Okay. So what exactly 2D scaling is? Any positive value can be used as scaling factor. If it is positive, then the size will be increased, and if it is if the value is less than 1, then the size will be decremented or the size will be decreased. But if the scaling factor is equal to 1, that means it will remain uniform and at the same location. Okay, so there are three types of scaling: either it is increasing, it is decreasing, or it will remain same. Okay, so if scaling factor is less than 1, then object moves closer to the origin, and if a scaling factor is greater than 1, then it will be object moves farther from the origin. Okay. Now this is some artifacts or some problem solving on scaling. So how easily we can represent the scaling is, and it is a change of object that we already discussed, and S or Sx or Sy is the scaling factor in x and y direction respectively. So Sx, if we multiply it with the old coordinate value of any point P, so x into Sx, that will determine the new value of x. So x dashed is the new value, so x dashed is equal to x into Sx, and y dashed is equal to y into Sx. So this is how the calculation is done. And if we more generalize, if the final point that is p dashed, so p dashed can be calculated as p into s of x comma y. So let's take an example. This is increasing, means this is a scaling, positive scaling we can say, and this is a negative scaling, that means it is getting smaller in size. Now let's take an example problem. Initially p point having coordinate 2 comma 3, so this is the coordinate, and scaling factor is 2 comma 3 again. Then what will be the coordinate of p dashed? So the initial values, that is x and y values, that is given. So 2 and 3, these are the values of x and y, right? And we have to find out x dashed. So x dashed is equal to 2 into Sx. The value of Sx is 2. So 2 into 2. And to calculate y dashed, we need the y value, that is what, 3. It is given here. We'll multiply it by Sy, and the value of Sy is again 3. So if we calculate it, it yields 4, that is the value of x dashed, and it is 9, that is the value of y dashed. So that is how the answer is 4, 9, right? So this becomes the answer after the scaling of any point P, and when it reaches to a new point after scaling, so it is a positive scaling. That means the Sx and Sy values are greater than 1. That is why it is a positive scaling, and the size will definitely increase after scaling. So this is all about these three things: the homogeneous coordinate that we have discussed at the beginning, different types of 2D transformation. To summarize, today we learned about three things of 2D transformation. The first one is translation, next one is rotation, and the third one is nothing but scaling. So keep learning, and this is a problem for you. If the scaling factor is 0.5 and 0.33 for these 2 points, what will be the final point? So this is the answer. but I would expect that you will do it yourself. Thank you so much. So keep watching the next video where we will discuss about the shearing and reflection.